So we deduce that. So we are getting DLB and before that ARD. So ARD and DLB, it means what? A comma B belongs to R composition L. So it implies that L composition R is a subset of R composition L. Similarly, we can show that R composition L is a subset of L composition R, correct? Hence, L composition R is equal to R composition L. So in this way we have proved. Now you see, as we have if all of you remember in unit 2, in corollary 1.5.12, what we have proved. Let rho and sigma be equivalences on a set S such that rho composition sigma is equal to sigma composition rho. That is when rho and sigma commutes with each other, correct? Then what is the rho join sigma? Rho join sigma will be rho composition sigma. So from here we can deduce by corollary 1.5.12 what is D? D is what? L join R. And when L R commute each other, we can say that this join is what? L composition R. Correct? So obviously we can say that L is contained in D and R is contained in D. And also you see D is L join R, and this is the smallest equivalence containing L and R. And also we know that L is contained in J and R is contained in J. How L and J are contained in J? You see, see, when you say ALB, it implies what? It implies and re-implies that XA is equal to B and YB is equal to A. Now it implies, re-implies that XA into 1 is equal to B and YB into 1 is equal to A. We can write like this or not? So what does it mean? It implies that X, these two are from S1. These two from the S1, correct? Your XY from S1. XY are belonging to S1, correct? Now here these two are S1 and these two from S1. So from here we can say that AJB. Sorry, it implies that AJB, not. So we started from here, XA into 1 is B. So what does it imply? It implies that A and B are J related to each other. Correct. So what does it implies? It implies that L is contained in J. Similarly, R is contained in J. So J is the equivalence relation containing L and R, and D being join of LR is the smallest equivalence relation containing L and R, since therefore this is the smallest equivalence relation containing L and R, so therefore D is contained in J. So these are the relations, that is H is contained in L, H is contained in R, and L is contained in D, D is contained in J, like this. So these are the relation on a S cross S, S cross S. So on a semigroup S, this is the connection between these Green's equivalences. These all are equivalences L, R, H, D, J, and this is the connection between this. That is, H is contained in R because H is what? L intersection R. So being an intersection R, obviously it contained in L. Now there are some very small facts. In a group G, H is equal to L is equal to R is equal to D is equal to J is equal to G cross G. And in a commutative semigroup S, H is equal to L is equal to R is equal to D is equal to J. So these are the two facts which I left as an assignment for all of you, that if you talk about the group, isn't it, not semigroup, group. So if you talk about the group, so you see that H, L, R, D, J, all equivalence relations are equal to each other, and also they are equal to G cross G. So all of you have to prove this. Second one, that if you talk about the commutative semigroup S, so on a commutative semigroup S, all these equivalences are equal to each other. So today I stop here, and I hope that I will continue these lectures as I am improving. Thanks.